Acid-base equilibrium, the effect of solution pH on solution equilibria. In this tutorial, we will be going over the effect of solution pH on solution equilibria, solubility of a metal hydroxide in a basic solution, solubility of a metal hydroxide in an acidic solution, adding acid to a salt with a weak conjugate base, and then worked examples. Solubility and pH. The solubility of almost any ionic compound is affected if the solution is made sufficiently acidic or basic. The effects are most noticeable when one or both of the ions involved are at least moderately acidic or basic. General rule: the solubility of a slightly soluble salts containing basic anions increases as the hydrogen ion concentration increases or as the pH is lowered. The more basic the anion, the more the solubility is influenced by pH. Some common basic anions that are influenced by the increased hydrogen ion concentration include the carbonate ion, phosphate ion, cyanide ion, sulfide ion, hydroxide ion, and fluoride ion. Example: predict the change in Zn+2 ion concentration when sodium hydroxide solid is introduced to the solution. Given the equilibrium system, ZnOH2 solid decomposes to form zinc ions and hydroxide ions, where ZnOH2 is a slightly soluble salt. The solubility product expression Ksp for zinc hydroxide is Ksp is equal to the concentration of zinc ions times the concentration of hydroxide ions squared. Claim: the concentration of Zn+2 decreases due to the addition of NaOH solid to the zinc hydroxide equilibrium system, as we see up here. As the concentration of the hydroxide ions increase in the system, the concentration of the zinc ions and hydroxide ion products will decrease relative to the amount of the ZnOH2 reactant. Qsp is greater than Ksp. The system will undergo a shift to favor ZnOH2 solid formation. The added hydroxide ions are consumed along with the zinc ions. The stress will be counteracted and a new equilibrium is established. Solubility of a metal hydroxide in an acidic solution. Students conducted an experiment comparing the solubility of zinc hydroxide in acidic water and deionized water. Predict whether container A or B will have the highest concentration of zinc ions. Claim: container B will have the highest concentration of zinc ions. Evidence: when the hydronium ions in the acidified water in container B react with the hydroxide ions present in the ZnOH2 solid equilibrium system, a neutralization reaction occurs, forming water. The hydroxide ion concentration will decrease. Reasoning: Qsp is less than Ksp. The system will undergo a shift to favor the formation of products, as we can see by this orange arrow right here. The ZnOH2 solid reactant will dissociate to replace the hydroxide ions consumed as a result of the neutralization reaction. The concentration of zinc ions will increase until a new equilibrium is established. Adding acid to a salt with a weak conjugate base. The fluoride ion F-1 is the conjugate base of the weak acid hydrofluoric acid HF. When the hydronium ion is added to this equilibrium system, SrF2 solid dissociates to form Sr+2 and 2F-1. The fluoride ion reacts with the added hydronium ion in the following manner. So here's the added hydronium ion reacting with the fluoride ion to produce hydrofluoric acid and water. As a result of this reaction, the fluoride ion concentration will decrease, as we can see right here. So the fluoride ion concentration in this reaction is decreasing due to this reaction right here. Qsp is less than Ksp due to the decreasing amount of the fluoride ion concentration. The system will undergo a shift to favor products. The SrF2 solid reactant dissociates and Sr plus 2 and F-1 product ions form until a new equilibrium is established. The solubility of the solid strontium fluoride increases as the concentration of Sr plus 2 and F-1 product ions increases in solution. Worked example. Given the equation AgOH solid dissociates to form Ag plus 1 ions and OH minus 1 ions. A small amount of potassium hydroxide, KOH, as we see right here, is added to a saturated silver hydroxide, AgOH solution. How will the mass of AgOH solid be affected? Justify your answer using the reaction quotient Q. Claim. The mass of the solid AgOH will increase. Evidence. Potassium hydroxide undergoes complete dissociation to its aqueous ions. KOH solid produces K plus 1 and OH minus 1 ions, resulting in an increase in the amount of K plus 1 ions and hydroxide ion products relative to the KOH reactant. Reasoning. Qsp is greater than Ksp. The equilibrium system will shift to consume the added hydroxide ions and form solid AgOH until a new equilibrium is established. Consider the compound MgOH2. Calculate the concentration of magnesium ions if the pH at saturation is 10.52 and the Ksp is equal to 2.06 times 10 to the negative 13. The chemical equation is MgOH2 dissociates to form Mg plus 2 ions and hydroxide ions. The equilibrium expression will be Ksp is equal to the concentration of magnesium ions times the concentration of hydroxide ions squared. The first thing that we need to do to calculate the concentration of the magnesium ions is to find the hydroxide ion concentration. We can do that by using the pH. So we're going to write pH plus pOH is equal to 14. We're going to rearrange the equation to solve for pOH, and then we're going to plug in our value for pH. 14 minus 10.52 gives us a pOH of 3.48. Now that we have pOH, we can find the hydroxide ion concentration using pOH is equal to the negative log of the hydroxide ion concentration. We'll plug in our value for pOH, and then we'll solve for the hydroxide ion concentration by taking the antilog of the negative 3.48 pOH. So our hydroxide ion concentration will be 3.31 times 10 to the negative 4 molar. Now that we have our hydroxide ion concentration and our Ksp value, we can solve for our magnesium ion concentration. So we'll start by rewriting our Ksp expression. We'll plug in our Ksp value and our hydroxide ion concentration value, and we'll solve for our magnesium ion concentration. When we do our calculations here, our answer is 1.88 times 10 to the negative 6 molarity. So to summarize, in a pH of 10.52, the magnesium hydroxide solid will dissociate until the magnesium ion concentration reaches a concentration of 1.88 times 10 to the negative 6. Now let's look at a situation with a different pH. Calculate the changes in concentration of magnesium ions and hydroxide ions if the pH of the solution was reduced to 9.0. So again, we're going to start out with our pH plus pOH is equal to 14 to solve for pOH. We will rearrange the equation to solve for pOH. We'll plug in our number for pH and solve for pOH. Once we have our pOH, we can solve for our hydroxide ion concentration using the formula pOH is equal to the negative log of the hydroxide ion concentration. We'll plug in our value for pOH and then find the hydroxide ion concentration by taking the antilog of the negative pH. So our hydroxide ion concentration is 1 times 10 to the negative 5 molar. Like the previous problem, once we have the hydroxide ion concentration and we have the Ksp value, we can plug this into the Ksp expression of Mg plus 2 times OH minus 1 squared. We'll plug in our values and solve for the magnesium ion concentration. Our magnesium ion concentration is equal to 2.06 times 10 to the negative 3 molar. In a pH of 9, MgOH2 solid dissociates until the magnesium ion concentration reaches a value of 2.06 times 10 to the negative 3 molar. This value is significantly higher than at a pH of 10.52. So what did you learn? We talked about the effect of solution pH on solution equilibria. We looked at the solubility of a metal hydroxide in a basic solution, the solubility of a metal hydroxide in an acidic solution, adding acid to a salt with a weak conjugate base, and then we went through some worked examples. Need more help? Feel free to contact me. Have a great day.